I am Satoshi Shuema from Kobe State College of Technology. Today, I talk about conversion of temperature rise in DC electrolytic capacitor for three-phase voltage FET inverter. Keyword: electrolytic capacitor, temperature, PWM scheme, and estimation of life. Let's start. I have divided my presentation into three sections. First, I would like to give you some background. Secondly, I'm going to talk about PWM schemes. Finally, I'll talk about experimental results. Let's talk about background. Generally, the life of electrolytic capacitors is 15 years. What happens when the temperature of the electrolytic capacitor rises? It will shorten capacitor lifespan. This is due to the evaporation of the electrolyte. This phenomenon follows the Arrhenius law. If the temperature rises by 10 degrees, the life is reduced by half. When the temperature rises by X degrees, the life is represented by this formula. Using the Arrhenius law, lifetime estimation is possible in a short period of time. Why does the temperature of electrolytic capacitor rise? That's because the electrolytic capacitor contains the resistance component ESR. If ESR consumes power, generates heat, then capacitor's temperature rises. Finally, electrolyte evaporates. Electrolytic capacitor has frequency characteristics. Temperature rise related to the waveform and frequency of the current flowing. This is because the electrolyte and ESR are frequency dependent. Is the temperature rise different or same depending on the PWM scheme used? Secondly, I'm going to talk about PWM schemes. By the way, inverters using the latest semiconductor material, for example, SiC and GaN. They are capable of high-frequency switching. Advantage: avoiding noise problems, low loss, and filter can be made smaller. Disadvantage: increased switching times and switching loss. Switching loss is a large percentage of switching element loss. Need to reduce switching loss. So, we focus on the two-phase PWM scheme. A variety of PWM schemes have been proposed, including a general three-phase scheme and a two-phase scheme. Advantage: two-phase PWM schemes can reduce switching times and switching losses than three-phase PWM scheme. So, two-phase PWM scheme is expected to improve the efficiency of circuits. Disadvantages included in AC voltage and current harmonic or carrier frequency band dispersed over a wide frequency band. We explain about D3 PWM and D2 PWM. This is a PWM model wave. AP, BP, and CP are switching patterns, and ID is flowing current DC side of three-phase voltage FET inverter. Furthermore, we assume that the magnitude of current flowing in each phase is in proportion to the magnitude of difference value. D3 PWM scheme using WH carrier wave. Total number of D3 switching times is 6 times. D2 PWM scheme using WH carrier wave and suppress one-phase switching by shift difference value. D2 L-phase switching poses. Total number of D2 switching times is 4 times. D2 PWM can reduce switching times and switching losses than D3 PWM, but D2 PWM disperses harmonics because D2 reference value changes stepwise. Next, I explain about P2 PWM scheme. Red here is 3-phase PWM using single-edge carrier. Let's focus on the period of all switch off. At past this period, then a phase switching poses. P2 PWM can reduce switching times and switching losses. P2 PWM doesn't change reference value stepwise. Therefore, the dispersion is reduced. Finally, I'll talk about experimental results. This is the experimental circuit 3-phase voltage fed inverter. We consider electrolytic capacitor connected to DC side, film capacitor connected to DC side too, because it has a good frequency characteristic. We measure flowing current of electrolytic capacitor and temperature. Experimental condition, switching frequency is 6 kHz. Modulation ratio is 0.85. Output power is 5.7 kW, and output frequency is 15 Hz. This is the thermostatic bus. This is the inside of the thermostatic bus. Controller, electrolytic capacitor, driver, and inverter. This is the result of electrolytic capacitor's temperature. Thermostatic bus operates 15 degrees. At the start of the experiment, the temperature of electrolytic capacitor must be the same. Therefore, only operate the thermostatic bus for about 60 minutes. Next, main circuit operates for 180 minutes. Capacitor's final temperature D3 is 23.0 degrees. D2 is 23.2 degrees. And P2 is 23.4 degrees. Delta T is temperature change of capacitor, equal final temperature minus first temperature, 15 degrees. Delta T is used for life estimation. For all PWM schemes, capacitor's temperature rises about 8 degrees from initial temperature. Let's calculate capacitor's life by using Arrhenius law. Substitute delta T for X. D3 is 0.574. D2 is 0.566. P2 is 0.559. If capacitor temperature doesn't change, this index is 1. D2 life is 1.01 times longer than P2. D3 life is 1.01 times longer than D2. From these results, life of electric capacitor only slightly changes. However, If you want to use the electric capacitors longer, you should run the circuit in D3 PWM. This is a frequency analysis of the current flowing through the capacitor D3, D2, and P2. All PWM schemes have a large current value in integer multiple of the carrier frequency 6 kHz, 12 kHz, and 18 kHz. Let's compare D2 to P2. D2 has widely dispersed harmonics and includes log-order harmonic. However, P2 suppresses harmonics. Conclusions: proposal scheme P2 suppresses harmonics than D2. Life of electric capacitor only slightly changes D3, D2, and P2. Suitable ones change the switching frequency and apply PWM scheme injected third harmonic wave. Thank you for listening to my presentation.